Hello, everyone, fellow peers, professors, and those who are just interested. My name is Shania Channon, and today I'm excited to be sharing with you my preliminary seminar for my master's dissertation. Firstly, I just want to quickly acknowledge my wonderful supervisors, Professor Sermon Murphy and Shishir Dalakia, and together we've designed a project that searches for pulsating white dwarfs with red dwarf binaries in our local stellar neighborhood. So just quickly, I'll go over a brief agenda for the talk today. We'll cover why this work is important in the astrophysics world, along with some background information and related work. And then we'll move into the specific aims of the project, followed by research design and, of course, our expected outcomes at the end. Alrighty, so let's get cracking. So why is this topic so important? Well, in order to frame this correctly, I might have to actually jump ahead a little bit and give you some background information first. So what even are white dwarfs? Well, all stars that are around 8 times the mass of our own sun or smaller, which makes up around 97% of our stars in our galaxy, will turn into a white dwarf. They are the end stage of a star's life evolution. So this process of turning into a white dwarf is actually super common and also super important to understand. Now, pulsating white dwarfs are slightly different, but still very important because they let us see inside the star in a way that's usually otherwise impossible. So through astroseismology, which is the process of studying a star's tiny rhythmic brightness changes, which looks like breathing, it looks like this. The core gets hot and inflates and gets brighter, and then it cools, deflates, and gets dimmer. So by measuring this breathing action, we can infer things like their internal structure, chemical composition, and even how they cool over time. Different internal compositions of a star and the resulting different physical behaviors associated with them cause all different kinds of pulsation modes. So different types of this breathing that we can see here. And kind of like a fingerprint, they can tell us about the different layers and mechanisms inside. So if we can observe the pulsation of a white dwarf, we can find out what's going on inside. And like I stated before, if 97% of our stars end up here, it's an excellent way to further our understanding of how stars, just like our own sun, operate, evolve, and eventually die. Current work by Althaus and Corsico, who are the two leading researchers in this field, have identified 9 different potential types of pulsating white dwarf, all with different behaviors and pulsation periods. Well, now you might be wondering, well, if these white dwarfs are so important, why doesn't everyone just look for them? Excellent question. The trade-off here is that white dwarfs, relative to their younger, brighter neighbours, are just incredibly dim and usually very difficult to observe visually, as you can see in the Sirius image here. The white dwarf down the bottom is almost completely swallowed in light by its companion star, which is why one of the key ways to find them is actually to look somewhere else, which is what we'll be doing for this study. Most stars in our galaxy are actually in a binary system. And typically, if a white dwarf were to be in a binary with most categories of stars, the companion would be far too bright and noisy radioactively to ever find the white dwarf. However, red dwarfs are cool enough that it's possible to observe them, and with enough computational magic, find a hidden layer in the photometric data that we can see the pulses from the white dwarf, that breathing mechanism from before. Now, this white dwarf-red dwarf relationship is fascinating for a whole other reason. They have the potential to be ticking time bombs. In some binaries, the white dwarf slowly steals matter from its companion, like we can see on the right here. And if it gets too massive, approaching 1.4 times the sun's mass, otherwise known as the Chandrasekhar limit, it can explode into a type Ia supernova. These are some of the brightest events in the universe and are used in astronomy to measure cosmic distances. Currently, there aren't any of these supernova events nearby, so studying them and identifying systems that could have supernova potential could help us predict when and how these spectacular explosions happen. So in summary, why is this important? Well, 97% of our stars will end up as a white dwarf, and they are excellent tools for understanding stellar interiors, evolution, and interactions. Alongside this, due to their elusive nature, many of the white dwarfs in our local stellar neighborhood are undiscovered yet, so there may be new pulsation types or classifications of white dwarfs we haven't even found. If we are successful in finding white dwarfs, we can also assess them further for parameters associated with type Ia supernova. Now, with that information behind us, the aims of this project are relatively simple. We are hoping to take large chunks of data from the Space Telescope mission TESS, namely light curves of red dwarfs, and analyze it for frequencies we can associate with white dwarf pulsation hidden behind the companion. And hopefully we'll find some new white dwarfs along the way. Secondary to this, as an addendum item, if the findings from our first aim are substantial, the white dwarfs found will be run through a risk matrix and given a likelihood of future type Ia supernova. This will be a stretch goal and more of a template making exercise. M dwarfs, which are the red dwarfs we'll be mostly looking at, won't ever enter into a red giant phase and so won't be able to transfer enough mass required to reach the limit and go supernova. But this is a sort of beta test idea to potentially run on other systems in the future. I say secondary also as one of the key limitations of this project, among the others you see here on screen, is the complexity and difficulty in finding a white dwarf. While we will be processing up to tens of thousands of samples, in reality, the noise from the companion star and other background space noise may drown out the frequency of the white dwarf altogether, or the chunk of data taken from tests may just be in an area of the galaxy where there's little to no white dwarf evolution yet. So this second aim will only really come into play if there's enough findings to make a catalogue with. One other limitation I want to highlight is just a fact about working with space-based hypotheses and data, and that is time. Unfortunately, in the case of studying supernova, particularly in our local system, events such as type Ia might not happen for millennia, which makes testing models quite difficult to prove correct. So I just want to acknowledge that this secondary aim is meant to be indicative only and would likely be a good avenue for future projects. In terms of design, we wanted to keep this project fairly simple, and the basic workflow looks like what you see here on screen. So we take the test data, we apply some code and find the frequency of the white dwarfs and then record them. And then if there is enough white dwarf data, perform some secondary analysis to assess for supernova attributes. In reality, this flow is a little bit more detailed, and I've stepped out the main components here. The test data will come in large-scale format in the form of light curves, and a high-performance computer will be tunneled into and will be used to run the analysis. As there will be millions of data points being processed, which my little HP laptop can't handle. I've written a Python function, which is in the final stages of tweaking, to normalize the data, find signal detection efficiency of each light curve, and then identify peaks in frequency that are above that threshold, which, if we find any, will be correlated to a pulsating white dwarf. The function then performs a Lomsgargle analysis, which was chosen as it's more resilient to non-perfect data than a Fourier transform, and will then phase fold and bin the data to make it just neat and tidy. From here, the outputs will be analysed for those peaks, and any white dwarfs found will be catalogued against the test data, location, pulsation type, and category of red dwarf companion will all be recorded. If there are a substantial amount of entries found, additional analysis using the information we can infer from the type of pulsating white dwarf it is will be conducted to extrapolate the orbital period and distance of the binary, which will feed into a Bayesian network function and given a predisposition for type Ia supernova. These processes can be found in modern work, such as that by Althaus and Corsico. However, these methods, particularly the Lomsgargle transform, has been widely used in astronomy for the past 40 years, and they're pretty reliable ways of processing large amounts of time series data. Now, after all of this, what are our outcomes? Well, artifacts produced by this study will both be the function made to identify and normalize pulsating white dwarf frequencies and the Bayesian network made to assess likelihood of supernova. From these artifacts, the outcome itself is fairly simple. We want to identify new pulsating white dwarfs to add to the international registry. And if we're successful in that, then assessing them for type Ia characteristics and behaviours. The coding for the white dwarf hunting that's being used is based off several decades of trial, and the methods are used pretty widely in the astronomy field, so the reliability of this method is predicted to be quite high. The Bayesian network for the supernova is a little bit more experimental, and there's a risk that the model won't capture the data as well as we hope. Now, realistically, I also do have to acknowledge that we will probably never see one of these binaries go supernova in our lifetime, especially not with the systems we'll be looking at. However, highlighting a system's predisposition for this type of event is important to progress our knowledge and observations of supernova evolution, and constructing a test function to model that is also quite important too, which is why it's being included in this study as a stretch goal. And that brings us to a close. So in summary, we are honing in on the final stages of life of 97% of our observable stars and hunting undiscovered pulsating white dwarfs by taking light curve data from red dwarf stars and peeking behind the noise with a Lomsgargle transform to try and find those peaks of our white dwarfs. Then, if we're very lucky and we find some, we're going to make a Bayesian network to calculate how likely that binary system is to eventually go supernova based on orbital separation and period, which we can use to make a watch this space catalog for future supernova events. And with that, that brings this presentation to a close. Thank you so much for listening. And if you have any questions about the project, please feel free to reach out on my email here. Here are my references. Have a good day and thank you.